the communication systems course. Today we're going to have 3 guest lectures, and this is our first guest lecturer, Knut Åkesson, and he will talk on network control.
Okay, thank you. Let's see. So I'm from the same department, but from the division in systems and control. So my background is in control engineering, but I do most of my work today on manufacturing systems and formal methods. But I also do have one research project where we do testing of vehicles. We would like to do automatic test generation. So that's a very important area, you know, when the complexity of the systems increases, and then you have problems with the quality. So you need to figure out, I mean, you try to find out all the problems as early as possible. And we try to automate that by using the models we have in Simulink and similar tools. So let's see, while we're waiting. So we will talk a little bit about vehicles today. I don't know if I should. What I wanted to talk about today was network control systems in general. So I will talk both about vehicles and what you have in manufacturing systems. So I just wanted to start with some different trends that we see. So maybe you have heard about these 3 terms: cyber-physical systems, Industry 4.0, and Industrial Internet of Things. And they are very much the same, but it depends a little bit on which background you came from, which term you tend to use. But I think what they have in common is that they are all words that describe how system changes. And I think today the innovations in systems are mainly around these 3 C's here: computation, communication, and control. So, and they, of course, all relate to each other and depend on each other. So this is the course about communication. And communication is an enabler to do computation. Because if you have communication, you can get in much more data. And with much more data, you can use computation and control to come up with much better decisions. So you try to optimize the behavior of the system. And this happens within vehicles, but also within, for example, manufacturing systems. They are all much smarter these days. The Industry 4.0 is a German term that has to do with reinventing manufacturing in Germany, but it's happened in Sweden and in United States as well. So, yeah, so communication is a really important technique here. And I will focus a little bit on control applications. And in a control application, you have a network between the physical plant that you control, the vehicle or the manufacturing system, where you have the actuators and sensors physically attached to it. And then they are connected to a control network, and then you have one or many different controllers that take in the data from the sensors. They do some computation or implement some control strategy, come up with a decision that they send to the actuators. So if we now take a car as an example. So in this case, we see the architecture for it's a picture from Volvo actually. So you see here that we have up here we have the main communication, we have a GPS, we have some DSRC, that's communication for vehicle to vehicle, short distance communication and long distance communication. And then within the car you have a number of different subsystems here that are different in nature. So for example, we have the powertrain that includes the engine and transmission. For example, we have the chassis, we have the brake, steering, and so forth. And then we have electronic modules like the different instruments, different doors, lights, climate control, etc. And then the head unit, which includes the audio and video and so forth. And they all have very different needs. So here, for example, if you have video, you have very different needs. You have, for example, much higher bandwidth is needed here than if you do engine control, for example. And also for safety reasons, you would like to separate these systems so they can't interfere with each other. So for example here, it's very important that the engine still works and the brakes, for example, even if you change the volume on the stereo you have. So here we see an overview of the different subsystems and typically properties of those and the different kind of buses that is used. So for example, for the multimedia, there is a bus. It's a fiber-based bus called MOST with a relatively high bandwidth. But what is critical here is that the safety requirements for this is very low. And for example, if you compare this to the powertrain, where you have different variants of a CAN bus, where you have typically low bandwidth, but on the other hand, it's very important that if you send a message that it arrives within a specified time, so that you can trust it. And you see here that for the body and comfort and the chassis, they are all CAN-based, and then there is another SI bus here for the safety. These, the data here are from a BMW 7 Series car. Yeah, maybe before that. So if you go out and have the XC90 vehicle, you will have about 100 different electronic control units. And you will have maybe 5 different buses. So there is for the different subsystems. So they all communicate with the different electronic control units. If you then go to a truck, then you have an even larger number of different networks. So typically between 16 and 19 different networks. And about the same number of lean networks. That's another type of very easy or simple network protocol. And then you can have Ethernet and Wi-Fi on the truck as well. And then you have a lot of parameters that can be turned on and off. So for example, there are about 100,000 different parameters that can be set in a truck, and about 22,000 different signals that are logged while you're running the truck. Okay, so what are the advantages with having these different networks? Of course, reduced cost is the main factor here, because you can have less wires. And if you have less wires, then you can also increase the reliability by having fewer contact points and so. And it's very modular approach. So if you need to hook up a new CPU or a new sensor, you just connect it to the bus. and then with the bus it then becomes very easy to share the information. However, but there is also a price you pay by having a network instead of just connecting the sensors and actuators directly to the microcontroller. And one thing you get is latency. So you have a delay. So after you have the data has been sent from the sensor, it will take some time before it has arrived to the electronic control unit. There is also another problem that is related to the delay, and that is that the delay differs. So at one time it can go very fast, but in another instant it can become much slower. And this makes it very hard to analyze the closed loop behavior of this. Because I think most of you have taken the basic control course, right? So you know stability, for example, is an important thing. And typically we know that if you have delays, that's bad for stability because it introduces extra phase delay. And phase delay are bad for the stability because the phase margin decreases. However, if then the delay is different from time to time, then it becomes even more complicated to analyze. Because if it was constant, then you could sort of include it in your analysis. So pretty much in control applications, you would like to decrease the latency and get rid of the jitter as long as it is possible in order to be able to analyze the system. So just to show you what I think you recognized from a basic control course. So you have a process that's to be controlled, and then you have the AD conversion and the DA conversion. So the AD will read the analog signals and generate a discrete time sequence of signals that will then be used to form an error that will run through a control algorithm and generate a new output that then goes through the DA conversion and will affect the processes. But in the basic control course, you had a number of different assumptions. For example, you assume that the sensors here in the control algorithm that they are sampled with the same sample time. And you also assume here, for example, that the control algorithm is infinitely fast and that you always get fresh data. So there is no time delay from when you can measure the data until it can affect the control algorithm. However, but that is not how it works in practice for a various of different reasons. One reason is, of course, due to the network, because there you have, as we said, many different electronic control units that are connected to the same network. And I think as you have discussed in this course, you know that if one computer is sending data, then another computer has to wait until the first one has finished. Or if they have some other mechanism to handle the priorities between different messages. But the network was one thing. The other thing is that in every microcontroller you can have not only one task that is running, but you can have multiple tasks. So different control algorithms that does different things. So that means that they share the processor and then they share it in time. So for a short while, one control task will be executing, and then the other control task, they have to wait until the first task is finished, and then it can be their turn to execute. And of course, this introduces both delay and jitter, which is problematic. So this is what it can look like So here we have 3 different times. So this is basically the time between this and this is the sampling time. So the control algorithm should be updated, let's say with 100 Hertz. So every 10 milliseconds it should be a new control signal should be updated. But if you now consider a single control task, it might be that while it is ready to run here, it will take some time because the processor might be busy doing something else until it starts to execute. So then it can start to execute for a while. Then it might be preempted by some higher priority task. And then eventually it will be completed. And at this point, it will try to send data over the network. And depending on, then basically you have the same problem on the network then. Because is the network idle or not? There can be some other microprocessor that is causing the network to be used. So that's why we talk about the latency and we talk about the jitter. So the latency was basically the time until the input-output latency is the time from you read a value until it has affected the output. So the time from you read something from the sensor until it has affected the actuator. And basically the jitter is then the maximum input-output latency minus the minimum input-output latency. So that is how much it varies. So both of those are important to get control of. So what is this? So if we then look at control systems, so how are they different from the type of networks that we use every day, like Ethernet networks? So typically it's not that much data that we need to send. For example, we have a sensor, it will read some value. And that could be a 10 or 12-bit value, but not very little data. But we need to read it periodically, because we should update the control signal periodically. So we read the data periodically. And as I described before, we would like to have low latency and small jitter. And other things that can make it more complicated is that you can have also sudden events, so aperiodic requests. For example, that some subsystem will signal that something has gone wrong. So you need to take some action. For example, there is a problem with the engine, you should stop. Or there is an accident going on. We need to do something very quickly to, for example, blow up the airbag. And then you have the other real-time data. Typically, you would like to log the data, so you can do this, for example, in a post-accident investigation. You can see what happened. So I will say a few words about a very common bus. It's called the controller area network. So it's a relatively simple bus. It was developed in the mid-1980s, but it's still used very frequently, both in vehicles. So we talked about the cars and trucks, buses, but it's also used in manufacturing systems and in process control applications. So it's a bus topology. So you have all the different controller nodes. They are attached to the same cable. And in its original formulation, everyone that would like to send can start sending at any point in time, but they can, so they will first see if the bus is quiet, so no one else is sending, and then if they start transmitting the data, and if two nodes then start to transmit data at the same time, they can detect that there is someone else that is sending the data, and they also have a priority, so they can figure out if I should continue to send data or if I should become quiet. So this is actually a relatively simple electrical property that makes this possible. But let's see if I can get rid of that. But this CAN bus is used to, it has a relatively low bandwidth, so about 1 megabit per second. It depends a little bit on the length of the bus. So the longer bus, the shorter or the smaller bandwidth you will have. And it's also built to send short messages of data. But as we discussed, we would like to minimize the latency and the jitter. So then there are different variants of this protocol. So one variant is the time-triggered CAN protocol. So while in the original formulation, in the original CAN protocol, every controller could start to send data at any point in time. But in case they start to send data simultaneously, there is an arbitration mechanism to figure out which one to shut or which one to silence and which one will continue. But with a time-triggered CAN, you have a predefined schedule. So you have set up the system so you know beforehand that you are the only one to send data at this point in time. And this is a very efficient way of making sure that you have a known latency and a known jitter. So I think we can see. So you divide time into different message cycles. So you have different message types. And then here you have a reference message used to synchronize the clock. And then you have decided beforehand that at this point in time, we should send message type A. So, and this could belong to electronic ECU5 that should send the specific message. And then when it's done, message C should send, and so forth. So this way, we will make sure that we have this known latency and jitter. And for these aperiodic messages, for example, alarms, we can use the arbitration mechanism. So at this point in time, any unit can send data. So, and this is very useful for if you have sporadic needs to send data. And as I mentioned, each message type has its own priority. So very important messages will have higher priority. So if there are two different electronic control units that tries to send data in this slot, it means that the one with the highest priority will continue and the other one will go silence. And of course, then you could try to synchronize. So this was for the network protocol. Then you could try to synchronize this with the controllers. So if you have multiple controllers that are executing inside one ECU, then you could schedule them so that the data will be ready before it should send. before the network is ready. So you have a combined scheduling problem for the control tasks and the network. So please interrupt me. 5 minutes left. Yep. So that was the CAN bus. And I wanted to say a few words also about Ethernet and TCP/IP. So while Ethernet is used a lot in ordinary computer networks, it's not used so much in industrial applications. And there is a reason for that. And one is how this system, for if multiple devices try to send data at the same time, there is no priority between the different messages. And if you look at the Ethernet frames, they have, so this is the Ethernet frame, and basically you have the source and destination MAC addresses, and then you have the data here, and it's between 46 and 1500 bytes long. So this is used for sending a huge amount of data. But as we said, for our applications, we do not have the high bandwidth requirement. But on the other hand, we need priorities, and we would like to reduce the latency and jitter. So all of these are not really fulfilled by standard Ethernet applications. So, but still there is a huge advantage with Ethernet, and that is that it's so widely used. So it's cheap. So then there has come up a new standard called EtherCAT that has tried to adapt this. So you will use the same physical hardware for Ethernet, but try to make it fit better for this type of communication between sensors and actuators. So it's a little bit different. So you have point-to-point communication. So these are the I/O modules, so input and output modules, and they are then connected to each other like that. So you will have data, so you will have an Ethernet frame, it will go in here, and then the slave will read it. The data will be passed on to the next, and to the next, and so forth. So with this setup, you can't have multiple, or you can't have collisions. So you don't need to worry about that any longer. So that's one advantage. But there is one more difference, and that is that you will have in the data here, in one Ethernet frame, you will have different telegrams. So you will have one telegram for each sensors and actuator. So instead of using a full Ethernet frame for a single sensor actuator, as you would use if you had a standard Ethernet setup. And this has some huge benefits. So you can get really, really fast data here. So if you implement this, you can get 1.35 microseconds per slave delay from that you read an input frame until it's sent to the output frame. And typically, in each slave here, you will read, and then you see, okay, was this telegram for me or not? And then it passed around and goes back here, and then you fill in the data. For example, if it was a request to read a sensor value. So, and this scales very well. So it's not used so much in vehicles, but it's used very much in manufacturing applications. So, to conclude, the different networks are different type of networks are necessary for different tasks. And for control tasks, we have relatively little data, we have short periods, and we would like to have a deterministic behavior. So it should behave the same every time. So we try to reduce latency and jitter. And then you can use, for example, time-triggered protocols to deal with the collision data that you have. And Ethernet has to be adapted to be useful. Okay,
All right.
thank you. So any questions, by the way? Yeah.
Does anyone have any questions for you? All right, then thank you for
Okay,
the presentation.
sure. Thanks.
if you put it somewhere here, it's perfect. Okay, so we have our second guest speaker for today. This is Jimmy Inge. We will talk about smart grids.
Yes. So, hello, and thank you for allowing me to come and talk. And you don't see anything on the screen. Yes. So, as I said, good afternoon. My name is Jimmy Embe. I'm a researcher at Division of Electric Power Engineering. You might know us from the beginning, and I'm part of Energy and Environment at the moment, but as you all might know, we are facing a reorganization, so I will also end up in electrical engineering or some other. And today I would like to talk a little bit about this need for ICT in electric power systems. This short introduction into the subject will be on a little bit higher level than the previous presentation. I will talk a little bit about the present, but also a little bit about the future. And I will start with the future because it's a little bit more fun than actually doing what's done today, because that's already done. So, what do we need to know about electric power systems? In general, we are facing a big shift. You might have heard of it. It has to do with climate change. It has to do with nuclear waste or risk of nuclear disasters. So we're introducing renewables, which means that production goes from controllable big ones to distributed like solar power, wind power, wave power, tidal power. Small ones that are scattered depending on the available resources. So that will make a change. It also means that we can't really control the production anymore, so we need to control the loads. And a big difference between those, and this has something to do with the need for communication, is that these are many more than these. For example, in Sweden, we said we have a lot of hydropower and nuclear power. They are together like 80-85% of the electricity production in Sweden. But they are quite few compared to the number of loads, as you might guess, because everything uses electricity more or less. And that means we need to control the loads. But how can we control the loads? Because at home you don't just want to turn things on and off or allow someone else to do it while you're watching your TV show or you're doing the dishes or whatever. But we also know that there is a change in the society that we're not that eager to own our products anymore. We would like to buy a service. So as long as it's fixed, we don't really care how. As long as it's fulfilled in all our requirements, of course. And this opens up new opportunities. And this is what we often call smart grids, the way to solve it. Smart grids is a made-up word. They are not much smarter than before, because a grid is mainly copper or aluminium, but still, there are more. But they are like collected in these kind of smart grids. So what is smart grids? As I said, it's a buzzword made up. Here are 3 big research institutes who has tried to define it. Engineers try to define things if they're not defined before. And as you see, a lot of them are discussing digital information, communication, and information technologies, because they see the need for it. And I will come back to that. And there are also other ideas why we have these smart grids. Because there are other benefits than just do this. The environment, of course, less losses. Less losses means less need for production. 8 to 10% of all electricity that is produced in Sweden never reaches any use. Okay, 90% efficiency, that's quite high compared to a combustion engine. But we're discussing 14 terawatt hours of electricity that never reaches. So if we can increase just a little bit of that, there is a lot of things that can be gained. Less land needed. Of course, we build power lines that require lands, but also substation. Raw materials, that's another issue in general that we try to avoid. Visual impact, that's another thing that we would like to do. So we would like to make our things a little bit smarter. Decrease electromagnetic fields, could be dangerous. We are quite certain of that. We're not 100% sure in general, but we think they are, especially for children. Also for economy, less losses is also economy things, and we try to, the idea is also try to utilize low electricity prices. What I mean with that is try to use electricity when it's the cheapest, when there is an abundant availability. So when the wind is blowing, we should try to use as much wind power as possible. Solar shining today, let's use solar power. Maybe not now in February, but during the summer. Regulating power, that's another issue. Because we know that we also always need a backup. Decrease the backup, we will save money. And less power lines, because they will also cost money. So what is actually smart grids about? It's about increased efficiency in the grid. So if we can do that, there is a lot of things we can save. Money is one of them, and that's the easiest thing, because if we save money, we can spend money due to that. So we can always spend money to save money, as long as the total is still positive. So we save more than we actually spend. So, and one thing is also that what we need to do is not really, we can't really rebuild the system. Communication systems, it's okay, it will be outdated anyway in a few years. But the existing electric infrastructure is so big and so expensive, so we can't really crap it and just restart it. And the installation time and the lifetime are very, very long compared to others. Ordinary lifetime is 50, expected lifetime is 50, 60, 70 years if you install a device. I mean, the big one, the power lines, for example, they could even last even longer. So we need to start using our existing infrastructure. We need to start there. And there's also another issue. We can't really just tear everything down. We're out of electricity for a few years, and then we rebuild it again. That's another issue, which might be a little bit clearer. From my point of view, as you said, everyone is defining this in his own way, so why not me? So I've done it also. So I've tried to divide the things the things we can do. First of all is to add new products into the grid. I mean, normally we invent something new, fancy thing, try to use it. For example, a solid state transformer. It's a transformer based on power electronics. We don't have to go into details of that, but if you'd like to know more, of course, welcome. We can use existing products into the grid, for example, battery storage. Existing products, that's something that is developed for one thing, and then we use it in the grid. I mean, battery is a very good example, because a lot of things is now spent on making batteries for vehicles, electric vehicles and hybrid vehicles. But the same technology can be used. And actually also the same batteries. Because we know that electric cars say, well, in a few years, how long can we run it? Maybe down to half of its capacity after a few years. Then we need to scrap the battery and buy a new one. It's very expensive, yes. But there comes a second life of the battery. Because in the grid, you can use it as a half battery. Because there is no really space issue. There is no weight issue. Because since everything is standing still, it's not really a problem as long as we have a solid foundation. So new products we can use. And then comes what I think is the most cool thing to do is actually new ways of thinking, changing in strategies, not do how we normally are doing things. And all these three will require or provide more information so we can use it more efficiently. The grid then. So what kind of communication do we have? I know it's a quite complicated picture, and I will try to go through it together with you. this is the grid, so to say. Transmission, that's the big one, the big lines owned by the transmission system operators. This 400 kV line, the big ones you see everywhere. Subtransmission, that is connected the transmission and try to distribute it into regions. A little bit smaller ones, but still quite big. Then we got the local grid, and that is distributed inside the regions until each block, because each block has its own low voltage grid or 400 volt grid. So we have an increasing size in grids in this direction. So what do we have in this direction? It's a little bit complicated. First of all, we've got an increased amount of data. The lower you go down in the size of a grid, the more data you got. Not because you sample faster, but there are so many more points where you measure and are able to control. Because down here you got more or less all loads. And that goes down to simple things like computers, camera, and those kind of things. So you have a lot more here, which of course will require a lot of data. So we will end up in a big data issue here. That will not be the topic of today, but still. So that's one issue. And here we have quite few ones, even though we sample fast. But it's relatively little data, so we can handle it anyway. The security is lower the further you go down, because if someone tries to destroy something or interrupts the electricity, it will affect only a few people. But if you interrupt the transmission grid and you turn off for a country, and if we, for example, takes down the transmission grid, so we just have to restart it. It takes approximately 8 hours to do that. If we are total blackout, it takes 8 hours to get back. To be able to do that, we will need, and that will show in our GMP, gross national product. It will have a huge impact on the country if we have to turn everything off one day. So therefore, the security is much higher, and you can also destroy quite a lot more if you start here. So the security will be lower here. The demand of speed will also be lower because up here we need it for protection and supervision and those kind of things. So we really need to do things fast. While here we have a lot more time to do things. We are not that in a hurry because it doesn't go that fast. Because if we should do something, it impacts much, much less on the system as itself. But the integrity is, of course, a major issue when it comes here. Because if you measure someone's electricity consumption, you can actually understand what they are doing, what is happening. There are special systems for that. So you can actually start looking at someone. I know on a legal perspective, measuring someone's electricity consumption is approximately the same thing as having a heat camera on your house. They are judged in the same level. And you don't want to be at home and knowing that someone is always watching you through a heat camera. That's not very nice. So what kind of communication do we need? For transmission, there is mainly protection, and that is done by designated fibers. That means they have their own fibers. So no other communication on that, and that is due to reliability and speed. I mean, he is talking of priorities stuff, yes. And this has so high priorities, you can't use any other communication in those lines. To be able to secure that you disconnect as small part of the grid as possible. I know we're out of time, but I would like to finish these slides before we take a break. And then we can also use controller supervision, and this is normally done by separate networks due to the security issue. Subtransmission, we also have protection for some important lines. The same thing about controller supervision, also separate. But then comes also measurements. That's a little bit part of supervision here. But here, on this level, measurements can be done through different kind of shared networks. Shared networks is something where someone else uses at least a part of the bandwidth. Could be done in many, many different ways. But it's not really their own. But you can't really allow control or supervision over that. Then we come to local grids. So control and supervision to the extent I actually have controller supervision, because this is quite low today due to several reasons. And normally they have their own separate network for this kind of control and supervision. Still, because even though it's a local area, you can make quite a bigger problem if you start messing there. So it's a security issue here. But measurements are still on a shared network. Then it comes to the thing that is close to you. Maybe something you are a bit more familiar with. And that is the low voltage grid, the 400 volts. And here we use measurements on shared networks. This is normally handled by the grid company. You all know you have a smart meter at home. Yes, you have, even though it might not be that smart, but yes, it can. And we're also looking for communication with or between customers. And we are using internet. And we will just heard about how internet works. So we know a lot of things can happen, but we are not really in a hurry here. And we need a lot of data. So why not use internet? So I have 10 minutes more, but let's have a break.
All right. So please be back in 10 minutes.